Hi, this is going to be phase 2 of the coverage of section 14.5. So what we've done previously is introduce the tangent vector, unit tangent, the principal normal vector, and the curvature. That is things we call T, N, and kappa. And coming up in this session, we're going to add two more things to that, which is the binormal vector, B, and the torsion, tau. The point really of these three vectors is to give us a local coordinate system that's on the point that's in motion. If you think of it as a vehicle, it's the tangent points in the direction of motion. The normal actually points in the direction of the center of curvature of the path. And the binormal is just set up so that it's perpendicular to those two. So we can jump right into the definition of the binormal vector. It's just the cross product of T and N. In that order. Just to beat a dead horse in a sense, if you're pointing your fingers along T and curl them towards N, your right hand is going to be your right hand's thumb is going to be in the direction of B, and that makes this little triple of vectors T, N, and B a right-handed system, just like I, J, and K were. I'm actually holding them in the same orientation that we would leave I, J, and K right now, except it's T, N, and B. Okay, right-hand coordinate system. So next, though, the thing that's going to be a little tough is to develop a good understanding of what we mean by the torsion on a space curve, and why we would even think about torsion on a space curve. So let me see if I can adjust the camera view so that you can see this little display I've got laid out on my table. Maybe without creating any video feedback for you. Take that away. So let's move the table down a little bit. That's better. All right, so what I've done is pick 2 points along the space curve, kind of a question mark shaped thing. And on at those points, I hot glued these little placards to my flexible space curve thing from my old drafting school days, drafting office days. What I have drawn on those placards is the direction of the tangent vector and the normal vector. So the tangent vector points in the direction of motion as you're moving down the curve, and the normal vector points in the direction of curvature. You may notice this particular placard, I labeled it with the words osculating plane. The reason for that is, at this point, way out here somewhere along the direction of N is the center of a circle that circle would just kiss the graph. Osculation is the Latin word for kiss. And it happens that one of my pot lids from my kitchen actually works perfectly for this. So you can see that's the osculating circle. In fact, it matches the curve very nicely. All we really require is that it's tangent and that the curvature of the two things match. But these guys are in line with one another for quite a while. Okay, and then farther down we've got another copy of a T and an N at a different point along the curve. And of course, if these two osculating planes at different points are parallel, as they are right now, what that really means is the entire graph, the space curve, is actually two-dimensional. It's laying flat in the plane. If I wanted to curve it up out of the plane, hold on, let me set some things aside. To get that thing to curve up out of the plane, let's hold this guy down and try to make this guy rise up off the plane. Well, if you get it to happen at all, you should notice that there's a slight twist now between it. If we imagine this placard going over to here, it's got to slightly rotate as it goes. That's twisting. That's the torsion. It's the misalignment between two adjacent, well, I shouldn't say adjacent, nearby osculating planes. How much did this this plane have to rotate as it moved from point A to point B. You know, and in the limit, we think of this as a differential change, and we'd get a differential amount of rotation. But yeah, so that's the idea. Torsion is what allows the plane curve to not be a plane curve anymore, but rather to become a space curve. I'm holding it up so that you couldn't see it. Sorry. The more torsion there is along there, the more misaligned those two osculating planes become, then the more it becomes truly three-dimensional. If they're very close to one another, it almost lies flat in the plane. And if they're parallel to one another, it does lie flat. All right, well, before we leave this little demo setup, I want to point you to some new terminology. There's a name for this plane that is sort of defined by the t and the n vectors. But then there is another plane. Let's rotate the view slightly. This other plane is perpendicular to that one. Well, there's many different planes that are perpendicular to that one. I could pop this in there in different places. But there's only one plane that's perpendicular to that one that contains the normal vector n. And done like this, I've got my TNB frame sort of evident to you. Well, this plane, perpendicular to, actually it's interesting, it's dead perpendicular to the tangential vector. This is 90 degrees to t. And the normal vector lies in this plane. And the b vector also lies in this plane, because it's got to be perpendicular to both t and to n, because of the way it's defined as a cross product. Well, this plane is called the normal plane. And finally, there's another plane, which maybe I can just roughly indicate it. Oh, this thing's glued down. Well, it's in here. It contains the tangent vector and it contains the b vector. It's the third orthogonal plane there. That one's known as the rectifying plane. All right, let's return to the view of the whiteboard and proceed. All right, so we've got everything that we're going to discuss in this chapter, except I haven't really nailed down exactly how we compute tau, the torsion. But we know what the binaural vector is. That's just defined as the cross product. T and n we've previously done. Kappa we've previously done. This TNB frame, that's when you have a triple of vectors that you can use as a local coordinate system. That's a shorthand for it. People call that a frame. I already mentioned it, but it doesn't hurt to repeat it a little bit. TNB is a right-handed coordinate system. And I just said coordinate system. Frame is really a synonym for system in that case. So a right-handed coordinate frame. Now, I noticed there's a historical note in the textbook about an alternate name for this. It's also called the Frenet-Serret. I'm going to get the guy's name wrong. I have always heard it called the Frenet frame. But in the textbook, they mentioned a second person. So I had to just go look this up, but that's the other fellow's name, Serret. Let me see. I think they mentioned the folks' name, Jean Frenet and Joseph Serret. So I think that this is what I'll probably most often call it, because just Frenet frame, because I didn't know about this other person's name being associated with it. And it's just, that's what I was taught way back. So call it TNB, call it Frenet. Let's just try to imagine a image of it. We've got some space curve. Let's try to use colorfulness here. We'll have a green t vector. Now that should be unit length. I guess I'm using the span of my fingers as unit length. There'll be a normal vector. Let's make that one red. And you can't tell it, but this is curving away from us a little bit right now. So that normal vector is going back into the distance, into the board. And then B is going to be finally a blue vector that's perpendicular to the two of those. Well, when you have a system of three vectors like this, think about it with your fingers, they define three planes. And I just was showing you them physically on those little placards that were hot glued to my, my bendy curve. The T and the N vector, they define this thing we call the osculating plane. Let's keep track of these guys. Can we kill the naming of everything? T and N lie in the osculating plane. What's the normal vector for the osculating plane? It's the third one that's not mentioned. B would be the normal vector. Let me just write perp vector. I don't want to confuse you with the two uses of the word normal vector. We do talk about the normal vector n, and then there's also the normal vector to a plane. So let's just say the perp vector. Does that make sense? And I already mentioned the plane that includes n and b. So b, n and b and n lie in the the normal plane. I sort of meant to underline the terms that I was defining. So osculating plane is the one that has b and n in it. It's t and n, and it's perpendicular to b. B and n lie in the normal plane. That's the one that's perpendicular to t. So that would be t is the perpendicular vector. And there's one more. Let's see. We've got T and N. Maybe I should draw them in perspective. That's T and N, or at least a piece of it, and that's the osculating plane. Here's N and B. Those guys lie in the normal plane. There's a third plane, which if I try to draw it with the vectors here, would hide the other guys, so these lines become hidden. If that was a plane sitting in front of them. And that is the rectifying plane. So having kind of given you the image there of the three planes, I think I can get rid of this illustration and go back to actually listing things, because I need more space. All right, so T and N, B and N, the last possibility is N and B, isn't it? No, I've already done N and B. I've got N with both of the other things. There we go. So it's T and B that are sort of missing. T and B. I'm forgetting my arrows, my vector hats on things, so just double checking to see which ones have it and which don't. Got it fixed now. T and B lie in the rectifying plane, and then the normal vector is the third one of the triple. It would be the perpendicular vector will be N. Left the E off. Okay. Well, this is mostly terminology that, it doesn't hurt to know. But the only one that we usually tend to concern ourselves with is actually the osculating plane. That's kind of the bigger deal. But the other ones, you should know what they are. The normal plane is certainly not bad. It's being perpendicular to the tangential direction. It's sort of it's your peripheral view. If you're looking down the curve, it's everything that's at the edge of your sight. That's the normal plane. And the rectifying plane is the one that if you're going to lift off into the air, your tangent vector moves in that direction. If you make your tangent vector move towards B, that's takeoff when you're like in an airplane or something. Well, you'll remember seeing this prop before. I've changed it slightly by taping in a little placard to indicate one of the planes we've been talking about. Now, and I've got things labeled with x, y, and z, but think of x as your tangential vector, y as your normal vector, and z as the binormal. What torsion is, if you think about it, is how this frame is turning around the direction of motion. It's this kind of deal. The space curve would be passing along through here in the direction of this x vector, the t vector, really. So torsion is this. It's how much does this rotate as we move a little bit down the curve? Thinking about moving back and forth along the curve and seeing that amount of rotation. It's, well, it's complicated, but basically it's how the normal vector is moving or how the binormal vector is moving. They're both moving together as we go around this. It turns out to be easier to look at the rate of change of the binaural vector as we move a differential amount down the curve. So let's try to get through this derivation of what torsion is. Basically, to find it, we're going to differentiate the binormal vector with respect to arc length. We'll find the value of dB ds. Got ahead of myself. To determine torsion, which is written as a little Greek t, tau. By the way, it wouldn't hurt to just point out now that we've got three different t's going on. We've got the tangent vector t, we've got time t, and we've got tau t. And these guys are really easy to mix up. So make sure the crossbar for your tau's is on top, and the crossbar for your t's is definitely, in the midst of the letter. There should be a little bit of t sticking out above the crossbar here, but not so in tau. Okay, so to determine tau, we differentiate b with respect to arc length. I've got a spelling issue today. I don't know why. In other words, what I'm saying we should do is take the derivative with respect to t of the vector b. It's really a function of time as well, but I'm going to drop the arguments to most of these vectors. In other words, we find dB dt. But remember how b was defined? It's the cross product of t and n. So we could do it this way as well. d by dt of t cross n. And that's actually going to be more useful. Well, that's a product, so product rule is going to apply. And that means what we've got is, let's see, I usually do it the wrong order, so let me try to be careful here. It should be the first times the derivative of the second, so t times the derivative of the second. That would, look at me. I said I was going to differentiate with respect to arc length, and I did it with respect to time, right there. Yeah, not in my notes. My notes are correct. Sorry. Let's just fix these. Those t's should be s's. d by ds, d by ds. Right. That doesn't change because that's in the product rule the first thing unchanged, but the next thing is the derivative with respect to s of n. So that is dn ds. This is going to be a vector quantity. Derivative of a vector is a vector. And then we have to do the derivative on the opposite one, so we'll have the derivative with respect to s of t. That is what dt. That's a capital T. dt ds crossed with n unchanged. Now, something funny happens in one of these. If you think about where n came from, n was the derivative of t with respect to s, rescaled so that it had unit length. Yeah? Which means that this guy and n are just scalar multiples of one another. You remember that when we needed to figure out the normal vector, we took the derivative of the tangent vector and then scaled it till its length was 1. So these guys are parallel. They point in the same direction, or possibly opposite directions, but they you know, what's going to happen with their cross product? Whether they point in identical directions or opposite directions, the little parallelogram they form has 0 area. So these guys, that whole cross product there is 0. It's actually a 0 vector, I suppose, but it's still 0. Doesn't influence anything. So the derivative of b with respect to arc length is tangent vector crossed with the derivative of n. So I just cleared the board and recopied what we just derived at the top, so we have a little room to work. I want you to notice a couple of things about this vector dbds. There's really just 2 things that are going to be important. dbds is the cross product of things, so it's perpendicular to both of these guys. So let's just pick on the one we really need. dbds is perpendicular to t, the tangent vector. The other thing, though, because this is the derivative of a unit vector, b is of unit length, so that's that idea of constrained motion on a sphere. No matter what happens to the space curve, b is just always a vector that points, if you moved its tail to the origin anyway, it's a vector whose head is always on the unit sphere. So the derivative of a vector of constant length is going to be perpendicular to that thing. That's our second note. dbds is perpendicular to b. Any one of these unit vectors, if you take its derivative, you'll get something perpendicular to the original guy. So what does that tell you? If you're perpendicular to t and you're perpendicular to b, you must be going in the n direction. And I use that for parallel. dbds is parallel to n. Now, it need not point in the same direction as n. I don't want you to think that they have to be, pointing in identical directions. They could go in opposite directions. In fact, roughly half the time they do. But this means that this guy is just a multiplier of that guy. That is, dbds is equal to some constant times n. What we use for that constant is the torsion. So that K tells you how much the torsion is. And if you think about sizes, K times n, this constant times n, just scales n up to have the length K. So the length of that side is K. That means whatever this constant is, it's also the magnitude of dB ds. The problem, well, that's what I just said is slightly a lie. The problem is that the magnitude of a vector is always a positive number, and this guy can sometimes be negative, and we don't want to lose that sign. Let me pull back up my prop with the osculating planes drawn on it. You see, we could have torsion that makes the planes twist like that, or we could have torsion that makes the planes twist like that. And both of those happen. We call a positive torsion if it's going to curve in a spiral to the right, and a negative torsion if it's going to curve in a spiral to the left. I think I just do, yeah, that was positive. This is negative. If the spiral is right-handed, it's a positive torsion. All right, so this K here could be either positive or negative, because that K is effectively what the torsion is. But by long-standing convention, or that bit I just told you about the handedness of spirals, we actually need the number that goes in there to be the negative of the torsion. So dBds is a constant times n. It turns out we prefer to think of that as the negative of the torsion rather than just the torsion, but that's just a sign convention. If you didn't mind having left-handed spirals having positive torsion, we could just leave that as a T. Nobody does, but I guess people could have made a different choice earlier on in the world of differential geometry. All right, so we should do an example. Well, the easiest example is going to be a helix again. It turns out that if you do more interesting things, usually the expressions for the normal vector and the binormal vectors kind of get out of hand. And that's okay. We've got computers. We can't always just jump to a computer and get, be able to calculate effectively. But for the purpose of teaching, I think we want to have something where we can, not see a sort of algebraic explosion as we take derivatives. So let's keep our position vector to be the vector along a helix. I'll stick with a relatively easy one, cos t sine t t. Okay. Then let's figure out. Well, let's actually just sort of compute everything. We'll do the derivatives of r, so we get the velocity, the acceleration. I plan to get the jerk as well. And then we'll think about the tangent vectors and the normal vectors and the binormal vectors, and kappa, and finally tau. So when we take the first derivative of our position, we get minus sine t, cos t, and 1. The acceleration vector is the derivative of that, which is minus cos t minus sine t and 0. And the jerk vector is the derivative of the acceleration vector, which will be 2 minus signs, right? So that'll be sine t. Sine's derivative is cosine, so minus cosine, and 0. I want to get the tangent vector, but to do that, we're going to need to spot what's the length of the velocity vector. So that's really position, velocity, acceleration, jerk. Those are our first function and its first 3 derivatives. The length of the velocity vector, I'm going to drop the arguments here, just say the length of v. It's the square root of the sum of the squares. So it's square root of sine squared t plus cosine squared t plus 1. And because sine squared plus cos squared is 1, this whole thing ends up being root 2. Well, that lets us write down the tangent vector. The tangent vector, it is a function of time, but again, I'm going to suppress the argument. It's the velocity vector divided by this. So we could write it as 1 over root 2 times that velocity vector. Great. So, well, next let's get the normal vector. The normal vector is obtained either, well, technically it's defined as take the derivative of this thing with respect to arc length, but we've got a t parameterization in front of us, so we wouldn't want to use the definition here. Very closely related to that, the fact is that the derivative with respect to time and the derivative with respect to space are parallel to one another, so they just differ by a constant, and in the end we're going to divide by the length of that vector anyway to get a unit vector. So let's take dt dt. The constant comes along for the ride, excuse me, and we just take the derivative of the components there. Minus sine t becomes minus cos t. Cos t becomes negative sine t. And 1 becomes 0. Is there a vector we've done already that this looks similar to? No. Except for a factor of 1 over root 2, it's just the acceleration vector. dt dt. Now, how long is that vector? And you might think, well, gosh, I'd have a hard calculation to do to see that. But you don't, in fact, because combinations of cosine and sine like that, whether they have pluses and minuses in front of them or not, they're just parameterizations of a circle. So this is a circle in the xy plane, and it's constant 0 in the z direction, so it's literally a circle. Its radius is 1. You can tell that because there's no numbers in front of these. The minus signs don't count. Because the ordinary circle would be just cos t sine t, and this has minus signs on it, I guess it's sort of the point is moving around the circle like diametrically across from the point you normally think about, but it's still the same circle. And so I can tell you what the length of this vector is. It's 1 over root 2. And I'm just going to divide by 1 over root 2 in order to get the normal vector. So I can just barely fit this on the bottom of the board here. Our normal vector is just going to be minus cos t minus sine t comma 0. That's pretty nice. Well, I've got a whole board full of stuff, but I didn't get it all. I want to also get the curvature, and I want to get the binormal vector, and I want to get the torsion. So how do we come up with curvature? Well, you may recall we had multiple ways of doing that, but the easiest one to use in this scenario is take the derivative of t with respect to t, which we're looking at right here, and divide it by velocity's length, divided by this number, root 2. So take this vector, which is minus cos minus sine 0 with a 1 over root 2 in it, and divide it by another copy of root 2. I believe I've just said that poorly, because it's not just this vector, it's the length of that vector. So the length of this vector is 1 over root 2. We divide 1 over root 2 by root 2, and we get, well, kappa is a half. You know what I'm going to do? I'm going to erase starting at the top, and we'll fill in some of those things. The kappa that I'm searching for is defined as the length of the rate of change of the tangent vector with respect to arc length. So it's defined as that. But it is the same thing as 1 over the length of the velocity vector, the speed, times the length of dt dt. Again, these two vectors are parallel, and the speed is, or 1 over the speed is a constant proportionality between them. The constant that you need to turn one into the other is the speed. There's another formula we had for this. It's also equal, remember the simplified formula? You take v cross a and you divide by the cube of the speed. So that's interesting too. We could go back to v and a and figure out their cross product and try to work that out. But I think for us, that's the one to use. Because I've got d capital T dt, and I know its length is 1/2. Oh, sorry, 1 over root 2. And so just another factor of root 2 in the bottom makes this kappa. That's 1/2. All right, so then the other two pieces we need are the torsion and the binormal vector. Let's do binormal vector first. Then try to remember what elements I need to do the binormal vector. Here they are. I need t and I need n. And I'm going to do the cross product of those two things. Oh, yeah, right. I'm sorry, I was taking for a second wondering why there wasn't a constant out in front of root of the n like there is in front of the t. And the difference is that the t has something in the z coordinate where the n doesn't. So this vector here is already a unit vector, whereas this one is sort of unit in the xy plane, but that makes it a little bit long, and so we have to divide by something there. All right, so let's set up b. It's going to be the cross product, it's this determinant, ijk, t goes, I guess I might as well write out everything. It's mine. I may not have enough room if I write it that. Let me fill it in first and see what happens. Minus sine t over root 2, minus, I'm sorry, cosine t over root 2, and 1 over root 2. Those are the x, y, and z coordinates of that. So I didn't need to spread that out some. And then we need to write the components of the n vector under that. That's minus cos t, minus sine t, and 0. We ought to be able to do this cross product. I don't suppose I'll need these anymore. Let's see, okay, so the I component is going to be that little x here. Well, this factor times 0, so we don't really need to worry about that. And then it's minus this thing that has a minus sign in it. So I think the x coordinate is sine t over root 2. The y coordinate, it's 1 over root 2 times minus cosine, and then 0 times something times 0 we don't need to worry about. So that is negative cos t over root 2. What about the k? Well, it's going to be sine squared over root 2 minus negative, so plus cosine squared over root 2. Its length is 1 over root 2. If you don't quite believe me, just actually write it all out. Factor out the bits you can, and you'll see that it's 1 over root 2 times cos squared plus sine squared. And there isn't room for the ending bracket here, but imagine it just goes off the board here. So there's our b. You could, if you would like, check that this vector is actually orthogonal to the other two. It certainly should be. You could do that with a dot product, for instance. So remember the way to get the torsion. It comes from taking dB ds and seeing it as a multiple, negative tau times n. Another way to think about this is it's the projection of dB ds on the direction of n. That's what minus tau is. And since n is a unit vector, dB ds may not be, you can think of it this way. It's just do the dot product of n with dB ds. So I don't have dB ds yet, do I? I'm going to need to take that guy's spatial derivative. Well, I don't have the arc length parameterization, so I can't do it. But I can take the time derivative, and I kind of want to erase what I just wrote, but I also want to leave it. So, all right, let's do it this way. To get dB ds, we can compute dB dt, and Leibniz version of the chain rule, we need to have dt ds up here. That way the dt's would cancel, we have dB ds, okay, right? This is something we can compute, and this is just the reciprocal of our speed. So we are going to be able to figure out the dB ds by a sort of trickery. It's the same trickery we did to find n by taking a time derivative of t and then dividing by the speed. I made it look like we had to multiply by the reciprocal of speed, but you know, that's the same thing. Okay, let's try to do it. I'm going to do it right here underneath of its definition. dB ds is equal to, take the time derivative of those coordinate functions. The last one's going to be 0. Let's see, sine t's derivative is cos t. And the constant divided by root 2 just comes along for the ride. Minus cos t, when I take the derivative of cos, I get sine, and that'll be, wait a minute, cos, I get minus sine, so there's 2 minus signs there, that we get sine t. Also over root 2. And finally, when we take the derivative of the constant on the end, you get 0. So tau is this guy dotted with our normal vector. That's, I've erased the normal vector, but it's still here. It's kind of in hiding. Remember that the rows of this determinant we were doing are the t and then the n. So tau is the dot product of cos t over root 2, sine t over root 2, and 0 with minus cos t. Oh, I lied. I lied a little bit. Tau isn't this. The negative of tau is this. Negative cos t, negative sine t. 0. Right, so you can probably see that this dot product is going to work out to be, except for the 1 over root 2 part, it's going to be negative cos squared plus negative sine squared. So it's going to be negative 1 over root 2. Well, what does that mean? Tau is positive 1 over root 2. So that's everything, isn't it? We got the t, n, and b. This is t, this is n, and b is this one. We got kappa, which was a half, and we got tau, which is 1 over root 2. And the fact that tau ended up being positive means that this spiral we're talking about is of the right-handed sort. It's actually spirals. Sorry, I should draw it like this. It curves in a right-hand way. Okay, one last little tidbit, and then we're out. Do you remember the this version of things we had for the curvature? Well, there's a formula like that for tau, which is pretty cool. I don't know that I've ever actually used it in practice, but I like the fact that this thing exists. So I guess I'll show it to you. It's in terms of this one is in terms of velocity and acceleration. The thing we get for tau is in terms of velocity, acceleration, and jerk. All three of them come into it. So here it is. Tau is a vector triple product. Velocity cross acceleration dotted with jerk, divided by the length of the v cross a, which power is it, squared, divided by the length of v cross a to the second power. Oh, I've left off vector hats. Which is, I don't know, that's pretty strange, but that works. That is a direct way to compute tau. Some people prefer that. I'm not sure that I do. But yeah, there we go. All right, so that's it for section 14.5. That was such a big section, it ended up being in 2 days worth of lectures.